Hello everyone. My name is Mohammod Minhajur. I'm a PhD student at Case Western Reserve University, and today I'm going to talk about our recent study on Phytic behavior of concrete beam strengthened with the composites. So first, some background and the motivation behind our work. So around the US, the transportation structures are deteriorating day by day, and they need some sort of replacement or some repair. And it's always a more sustainable and cost-effective solution to repair or strengthen an existing structure rather than uh, totally replacing the structure. So two of the most common processes or materials used in the strengthening process are for fiber reinforced polymer, FRP, and fiber reinforced cementitious matrix, so that is FRCM. Though for FRP is an option, it comes with some disadvantages as well, like low glass transition temperature and difficulty in application, especially in the wet surfaces. So in that case, FRCM, it makes FRCM the better choice. There are many studies on FRCM in quasi-static loading condition, but there are very few studies which explore the fatigue behavior and where our study comes. Uh, so the outline of my presentation is I'm going to talk about the materials that we use, the test setup, and the test results from the single lab check test in quasi-static loading with two different FCM width, also different orientation of the PBO fibers. And then I'm going to talk about the fatigue test results and finally the conclusions. So here we have the compressive strength on the left, compressive strength graph on the left, which is on the y-axis, we have the compressive strength of the concrete substrate, which is plotted against the edge. And as you can see, the concrete substrate, concrete has gained strength over the time and it almost made a plateau at the end. It should be mentioned that the FRCM was applied on the concrete substrate after 190 days from the casting of the concrete specimens. Then on the right side, we have the fracture responses from our fracture test. So we did this fracture test on the cementitious metrics that we used in the FRCM to determine the flexural strength and other fracture properties for future research prospects. To this purpose, we made two 3 by 3 by 10 inch specimens out of the cementitious matrix, and also we made one from the regular concrete. Then we cut a notch at the middle of those specimens and attached a clip-on gauge to basically measure the crack mouth opening displacement. And then we use a typical three-point bending test setup and control the test with this constant CO-mod rate. And by controlling the test with a controlled CO-mod rate, it allowed us to explore the post-bit behavior of these materials. And as you can see, the cementitious matrix, which are the blue and the red curve, has almost half of the peak load of the regular concrete. But in terms of deformation, it can sustain a lot deformation compared to the regular concrete. And part of the reason is that it performs like that because there are tiny fibers within these cementitious matrix that we use. So for our FRCM, the fiber we are using is a PBO fiber, which comprised of the longitudinal fibers and transversal fibers on one side. We use the typical single lab trick sheet test setup. We measured the loaded end displacement at the very beginning of the fiber with the help of 2 LVDT. And for the static test, we control the test with these LVDT measurements. So here are the results of the single lab trick sheet test in quasi-static loading condition. In total, we did 12 quasi-static tests. Out of these 12, 9 specimens were with a A4CM width of 2 inch, and there are 3 specimens where the A4CM width was 4 inch. Now, out of these A4CM with the 2 inch specimens, 8 were cast in a way that the PVO transversal fibers were facing towards the concrete substrate. And for one specimen, that is F09, the transversal fibers were put um, opposite to the concrete substrate. And as you can see clearly, the F09, which is this line, clearly performed better. So part of the reason it could happen is because for F09, the longitudinal fibers almost had a uninterrupted bond between the fibers and the matrices, and that could result in a better performance. So we followed the same orientation of the fibers for the next 3 specimen with A4CM width of 4 inch, and we noticed the load responses. And the load responses show that this time the load carrying capacity is almost twice of the previous 2 inch specimens, which makes sense, and which also proves the previous studies by the corresponding authors that there is no width effect. So here we have the same test responses, but this time the responses are in terms of the applied load and the global slip, where the global slip is basically measured by the 2L/BTT at the very beginning of the fibers. And as is expected, it has a steeper slope than the stroke, than the stroke responses, because there is less compliance here. For the fatigue test, we performed fatigue test. We looked into different loading range, 10% to 30%, and also 10% to 40% of the average load carrying capacity. And if you remember from the past graphs, there was a variability in the peak load as well. So we kind of took the average and counted that as well. And we also looked into different frequencies, 5 Hz and 1.5 Hz. And also we ran the fatigue cycle up to different cycles like 500K, 1 million, and 2 million. So here first on the left, we have a fatigue response from one of the specimens where the loading range was 10 to 30% and the frequency was 5 Hz. And as you can see from the beginning, 200K cycles and even in 2 million cycles, there can be, we can see that there is almost no damage or no change in the stiffness. And so after the fatigue test, we continue with the static test to kind of examine the response of the specimen. And we saw here is the fatigue plus the static test response, and we can see that it almost performed like an undamaged bond specimen. And then again on the right, we have another fatigue response from another specimen where the fatigue load this time is increased, and it's between 10% to 40%, and the same frequency, 5 Hz. Again, we didn't see any damage visually, and also from the graphs there was no change in stiffness. Again, we run the static test after completing the fatigue cycles, and we saw there it almost performed like a regular specimen without any damage in the bond. Next, we have another fatigue response again, and this time we used again a loading range of between 10% to 30%. But this time we decreased the frequency and we made it to 1.5 Hz. And as you can see, even with 500 cycles and decreased frequency, there was no damage in the bond. And eventually performed the static test, and it performed eventually even better than the other regular specimens. for a closer look at the Phytic cycle, here on the right, I have plotted the applied load with respect to the global slip that is from the LVT2 readings. And as you can see from here, a close look of the 100, 200, 320, and 500K cycles, there is little to no changes the stiffness, so basically no damage in the bond. Here I'm showing basically the Phytic cycle comparison between two different specimens. Here the loading range was same, that's 10% to 30% of the average load carrying capacity, but the frequency was different. The blue curves are with 1.5 hertz frequency, and the red curve indicates with the 5 hertz. So, and we plotted we tried to plot different cycles, the 100K, 200K, 500K, and 2 million. And what you notice that if we look into a similar cycle range like 500K, we can see that in 500K cycle, the 1.5 hertz specimen has a little bit less displacement compared to the one with 5 hertz. Now this can be explained from the static test results. If we see the static test results from 5 hertz specimen, that the load carrying capacity is much lower compared to the specimen with 1.5 hertz. So at 30% of the average load basically counts as a lower percentage for the 1.5 hertz specimens, and that could explain the less displacement in the cycles. So basically, in conclusion, we saw that the maximum loading capacity almost gets double as we double the A4CM width, and there is no width effect again. And then we also said that we also saw that the orientation of the PBO fibers actually it has an effect on the load carrying capacity as well. And we, from the fatigue test, we saw that even with the like 40% of the load carrying capacity, average load carrying capacity, and 5 hertz frequency, and with 2 million cycles, there was no visible damage in the bond. And the part of the reason that we didn't investigate yet the higher loading percentages, because that even with 40% of the load, we come up with a strain in the PBO that is 0.005, and which is already more than twice the yield strain of conventional river, which is 0.002 or something. So that is why we didn't increase the maximum load beyond 40% yet. Also from the fracture test of the cementitious matrix, we saw that the cementitious matrices for specimens can withstand larger deformation. Thank you. If you have, thank you for your attention. If you have any questions.